back to the online course on analog integrated circuits. In our previous class, we have talked about what is analog multiplier and some of the methods. Today, we will talk about a modified version of the emitter coupled multiplier, that is Gilbert multiplier cell. Before that, let's recapitulate some of the important points from previous class. Analog multiplier is a circuit which produces an output proportional to the product of the two analog inputs. That is, V0 is equal to K into Vx into Vy. An emitter coupled multiplier is a simple multiplier which uses emitter coupled pair and voltage dependent current mirror circuit as a current source. Here, one input is applied across the base of the transistors, that is VID, and another input Vi2 is applied to the current mirror circuit, and the output is taken across the collectors of the transistor. In this method, the change in collector current, that is delta IC, is equal to VID into K0 into Vi2 minus VBE on divided by 2VT. We know that the output voltage is proportional to this change in collector current. As the delta IC is proportional to those input voltage, we can say that output voltage is proportional to the VID and Vi2 minus VBE on. Or we can say that Vout is proportional to VID into Vi2 if Vi2 is very much greater than VBE on. This circuit have several limitations. The first limitation is that Vi2 is offset by VBE on, and the second one is Vi2 must always be positive, which results in only a two-quadrant multiplier operation. The third limitation is that the first input voltage VID must be very much less than Vt to make tan H of VID divided by 2Vt must be equal to VID divided by 2Vt. The first two limitations are overcome in the Gilbert cell. As I said earlier, the Gilbert multiplier cell is a modification of the emitter coupled multiplier which allows the four-quadrant multiplication, or it allows both the inputs to have signals in any polarity. Here is the circuit of a Gilbert multiplier cell. In this circuit, it consists of three different stages, with each stage having a pair of transistors. All these stages are emitter coupled transistor pair with cross coupled stage 1 and stage 2 in series with stage 3. Let us move on to the analysis of the circuit. Here we assume that all the transistors are identical and the output resistance of the transistors and the biasing current source can be neglected, and the base currents are also can be neglected. As we have seen earlier, the collector currents for an emitter coupled pair are IC1 is equal to IEE divided by 1 plus e raised to minus VID divided by Vt, and IC2 is equal to IEE divided by 1 plus e raised to VID divided by VT. Remember, when the positive of the input is connected to the base of a particular transistor, here it is Q1, then the collector current term will have the term e raised to minus VID divided by VT. And when the negative of the input is connected to the base of the transistor, then the collector current of the transistor will have the term e raised to plus VID divided by VT. Let's consider the emitter coupled pair in stage 1. Here, the current at the emitter coupled junction is the collector current of the transistor Q1, and positive of the input V1 is connected to the base of Q3, and the negative of the V1 is connected to the base of Q4. Hence, the collector currents are IC3 is equal to IC1 divided by 1 plus e raised to minus V1 divided by Vt, and IC4 is equal to IC1 divided by 1 plus e raised to V1 divided by Vt. Similarly, for the emitter coupled pair in stage 2, the current at the emitter coupled junction is the collector current of Q2, and the positive of the input V1 is connected to the base of the transistor Q6, and the negative is connected to the base of Q5. Hence, the collector currents of this emitter coupled pair are IC5 is equal to IC2 divided by 1 plus e raised to V1 divided by Vt, and IC6 is equal to IC2 divided by 1 plus e raised to minus V1 by Vt. And the collector currents of the stage 3 are IC1 is equal to IEE divided by 1 plus e raised to minus V2 divided by Vt, and IC2 is equal to IEE divided by 1 plus e raised to V2 divided by Vt. Apply this IC1 and IC2 terms in the previous equation. Hence, we obtain the expression for the collector currents as IC3 is equal to IEE divided by 1 plus e raised to minus V1 divided by Vt into 1 plus e raised to minus V2 divided by Vt, and IC4 is equal to IEE divided by 1 plus e raised to V1 divided by Vt into 1 plus e raised to minus V2 divided by Vt. IC5 is equal to IEE divided by 1 plus e raised to V1 divided by Vt into 1 plus e raised to V2 divided by Vt, and IC6 is equal to IEE divided by 1 plus e raised to minus V1 divided by Vt into 1 plus e raised to V2 divided by Vt. Here IL1 is equal to IC3 plus IC5, and IL2 is equal to IC4 plus IC6. Then the differential output current is given by delta IL is equal to IL1 minus IL2, which is equal to IC3 plus IC5 minus IC4 plus IC6, and which is equal to IC3 plus IC5 minus IC4 minus IC6. Rearranging this equation, then delta IL is equal to IC3 minus IC6 minus IC4 plus IC5. By taking minus sign outside from these terms, then we can rewrite the equation as delta IL is equal to IC3 minus IC6 minus of IC4 minus IC5. Apply the values of those collector currents, then we will get like this. Here, this IEE divided by 1 plus e raised to minus v1 by vt is common in these terms, hence we can take outside. Similarly, in these terms, IEE divided by 1 plus e raised to minus v1 divided by vt is common, hence we can take that outside. Therefore, the equation becomes like this. Here, this 1 by 1 plus e raised to minus v2 divided by vt minus 1 by 1 plus e raised to v2 divided by vt is common, and hence we can rewrite the equation as IEE into 1 by 1 plus e raised to minus v2 divided by vt minus 1 by 1 plus e raised to v2 divided by vt into 1 by 1 plus e raised to minus v1 divided by vt minus 1 by 1 plus e raised to v1 divided by vt. Here, this term will be equal to tan h of v2 divided by 2vt, which can be derived by the same method we followed in the last class. In the same way, we will get this term as tan h of v1 divided by 2vt. Hence, delta IL will be equal to IEE into tan h of v1 divided by 2vt into tan h of v2 divided by 2vt. As we have seen earlier, tan hyperbolic function will be linear if the magnitude of v1 and v2 is small with respect to vt. Then it will act as a perfect multiplier. In other cases, that is v1 or v2 is not less than vt or both are higher than vt, then the circuit have many other applications like modulator, phase detector, etc. Okay, so let me stop here today. We can continue in the next class with another topic.